Starting today with the first two problems, we're just looking for areas of each shape. For problem one, you could do it a couple different ways. Maybe you could look at it as like a triangle and a rectangle. That's one way to approach problem one, is to break it up by parts. Because I know like the area of a rectangle is base times height. The area of a triangle is going to be 1/2 base times height. So that could be one way to approach this. The rectangle would be 3 times 5.
Hey, we can't see your screen.
Oh, sorry. Let me share that screen with you. That'll make it easier, huh? Okay. So you could do the, rectangle is base times height. The triangle is 1/2 base times height. And you do 3 times 2 times 1/2, which would give you 3. So the total area would be 18 centimeters squared. Another way you could do it is you can do the area of a trapezoid formula, which is adding the two bases together, base 1 plus base 2, and you do 1/2 of that times height. That's another way you could do this area formula. Either one's going to work. They should both give you that answer of 18. In this case, the bases are 5 plus 7, and then the height is 3. So I get 1/2 of, is that right? Yeah, 5 plus 7. And then, height is 3. Yeah, so 5 plus 7 is 14, divided by 2 is 12, divided by 2 is 6, times 3 is 18, so 18 centimeters squared. Okay, so either method should get you the exact same area. You could do one formula, area of a trapezoid. If you remember that, that would be given to you on the IB exam too if you're planning on taking the test. Or you could do like area of a square or a rectangle and area of a triangle and then add them together. They'll both get you to the same point. Problem 2, area of a circle is pi r squared. In this case, we're doing 1/2 of the circle, so we're going to divide that answer by 2. So the radius turns out to be 3. So we'll do pi times 3 squared divided by 2. So I get 9 pi over 2, which comes out to, what did I have written down? Oh, I didn't do it yet. 9 times pi divided by 2, 14.14 centimeters squared. All right, so just practicing finding area. We're doing area right now just because when we start talking about integrals, the whole idea of doing integrals, which is the opposite of a derivative, is to help you find the area under a shape or a curve. That's the idea. Okay. Okay, so now problems 3 and 4, find the derivative of each function. For problem 3, we should get 3x squared plus 5/2. It looks weird because it's 5x over 2, but you could just rewrite that as 5/2 times x. And that's the way you can approach problem 3 there. Oh, and don't forget we want to write that as f prime of x equals. And problem 4, g prime of x equals 8x minus 1. All right, just for simple derivative practice there. Okay, that's the idea for these first couple of problems. Now, what we're going to start doing today is we're going to look at integrals, just the basic idea of them. And again, the whole idea of an integral is to find the area under a curve. So if I were to have a graph, and we'll just say, here's my function, and I want to say, hey, what's this area right here in the shaded region? That's going to be kind of hard to find. So that's the idea of integrals, it's going to help us find that area. Okay. First thing we want to look at, we'll just do a couple practice problems here. Problem one says, example one says, for this velocity time graph, find the distance traveled. All right, so it's velocity versus time. So you want to find out how long did this thing go, the distance traveled. Okay, and then for problem two, it says find the area under the graph. So this is another example of where you have this part right here and then this part, and we want to find this whole area of this shape right here. Okay, and we have this x equals a section, but because we have the line y equals 1.5x, we should be able to figure out what a equals to help us figure out if we want to do this with a rectangle method and a triangle method. All right, but that's the idea for problems 1 and 2. So I want you guys to try and work out problems 1 and 2 right now. Practice finding area for each of these. All right, we'll talk about them in just a second. Problems here. For example 1, I wrote it down already. We want to be able to find out basically like what's this value up here, because there's an intercept, and what's this value here at this intercept. So I just said let's set the x value equal to 0 and the y value equal to 0 respectively, and we'll figure out which one's which. So when we set v equal to 0, we find out that t equals 2. So that's saying that this length then would be 2 because we're starting at 0. And then when we set t equal to 0, we would get a 10 up here, which means this total length would be 10. And now we're just looking for the area of this triangle, 1/2 base times height. So 1/2 the base is 2 times the height is 10. And that's going to give us a distance traveled of 10 meters. So the area is 10, and that's what's representing the total distance traveled. All right. And that's just because this was a velocity graph before, which this is telling us our speed versus our time. So we can figure out what our total distance traveled is the total area under there, under this entire curve. Okay, that's the idea for this problem. Okay. For problem 2, it just says find the area under the graph. And for this one, we still need to find this. If we use the trapezoid formula, we either need to find this height. All right. Or I guess, yeah, we have the 3, y equals 3 there. So technically, I guess we could say this height is 3 right here. So we could use the trapezoid formula to do this and say we got one base is 5, but we still don't know how long the next base is. So we're going to need to figure out what a is here. And the way we can figure out a is figuring out where this thing ends when y equals 3. So I go ahead and plug in 3 for y, and I'm figuring out what x is at that point in time. Divide both sides by 1.5. I'm going to get x equals 2. So now I know that this total length is 5. This length would be 3, and we also know the height is going to be 3, and that's just because of this y equals 3 here. It's telling us that's where it's intersecting here on this axis. So trying to put this whole thing together to find our area. That's the idea for problem 2 there, example 2. So you do 1/2 of your two bases, base 1 plus base 2, times your height. Base 1 was 5, base 2 was 3, and our height was 3. So it becomes 4 times 3 is 12. So our total area is 12 units squared. Okay, so that's what integrals are all about, is finding area. Can we find the area under a shape? Now we're going to start with a lot of linear shapes today. We're going to look at one curve. We're going to look at this one right now. And it says, consider the area bound by the graph of the function f of x equals x squared plus 1. So that's what this equation is right here. It's a parabola x squared plus 1. And now we're going to try and find the area of this function between the lines x equals 2, x equals 0, and the x-axis. So first thing I want you guys to do is, looking at this, try and estimate the area. So use linear shapes to try and estimate what you think the area is. And write down your estimation down here. Okay, it does say discuss your method with a classmate. Hopefully we can talk about it a little bit in a minute here. But the first thing I want you to do, try and come up with a number for the area. All right, and then tell me, do you think, is it an overestimate or is it an underestimate for your guess of the number? Taking something like this, where we draw a bunch of rectangles in it, a shape we know how to find the area of, and then trying to calculate an estimate for the area. So notice that problem 2 here, I'm going to ask you to go ahead and do area of rectangles, and we just go ahead and drew a bunch of rectangles in. And we ought to ask first, what's the width of each of these rectangles? There's 4 rectangles inside this curve. The width of each one is going to be 0.5, right? I could do 4 divided by 2. That gives me 0.5. Or I could just look at it and say, okay, I can see this goes from 0 to 0.5. This goes from 0.5 to 1, 1 to 1.5, 1.5 to 2. That's the other way I could kind of look at this. But that's where the area, or the width of each rectangle comes from. It says, what is the relationship between the height of each rectangle and the graph of the function? So the best way to describe this one is kind of like the left-hand corner of each rectangle is on the left corner of each rectangle is on the function. And then for problem 3, we're going to do the similar thing, but we're going to see that the right-hand corner of each rectangle is on the function. So one of them looks like it's going to be an underestimate. The other one looks like it's going to be an overestimate. Now, I want to find a height of each rectangle. Well, first thing I can tell you, rectangle 1, the height is 1. That's pretty easy. How about rectangle 2? How do I find that y value there if I know the x value is 0.5? I can plug it in to the equation, and I can find that 1/2 value. So when the x value is 1/2, what's the y value equal on this curve? Because that's the left-hand corner. And that's what I want to do for this first one. So it becomes 1.25. That'd be the height for rectangle 2. Rectangle 2 height is 1.25. Rectangle 3 height, I can plug in 1, and I can find the height there. Rectangle 4 height, I can plug in 1.5, and I can find the height there. All right, so we don't need to guess on the height. All right, but that's the idea. So I want you guys to go and find the rest of the heights, and then find the area of each of the rectangles and find the sum of the area of the rectangles. Okay, so once you have that figured out, if you get that done, you can start working on the second one as well, where we have the triangles or the rectangles on the right hand side. Okay, so try those 2 now. For the first part, we find the values. We just plug in f of 1/2, we plug in f of 1, f of 1.5 to find the height of each rectangle. And then we just do base times height for each one, and then we add them all together. And I got a total area of 3.75 units squared. So our estimates before, we had an 8, a 6, and a 5 were a couple of the estimates. This time we got 3.75. We know this is an underestimate. And what we're going to do is we're going to call this the lower bound. All right, the sum of these areas will be a lower bound of the area of the shaded region. The area should not be lower than this number, 3.75 units. That's what a lower bound means. All right. We can do the same thing with these other triangles here using the right-hand side method instead. So doing triangles where their right hand ends up somewhere. Each width of each of these triangles is still going to be 1/2, 0.5. The height of each of these triangles, rectangle 1 this time is going to be 1.25. Rectangle 2 is going to be area height of 2. Rectangle 3 was 3.25, and rectangle 4, the area height was 5. It turns out they're the same numbers as above because they're still on the curve at the same points on the curve, so we don't have to recalculate anything. That's kind of nice. The only different one is the last one, which ends at 5. Then find the area of each of these and the sum. And for this one, I got a sum of 5.75 units. And this is an overestimate of the actual area. And that's just because there's a lot of shaded region that I'm including that I shouldn't. My rectangles are bigger than the area of the actual curve. But what I've done now is I've created a lower bound of 3.75 units and an upper bound of 5.75 units. So I know my total area is going to be somewhere between 3.75 and 5.75. And what this part's asking us to do is just go ahead and write an inequality relating to the lower bound, the area, and the upper bound. So we can say the lower bound is less than the actual area, and that's going to be less than the upper bound. So S is less than A is less than US.
So the lower bound is less than the area, and the upper bound is greater than the area?
Exactly, than the actual area, because the upper bound was an overestimate and the lower bound was an underestimate. And this is actually how mathematicians first created calculus, was they kept doing this method and said, hey, let's try it with 4 rectangles. And then they did the next thing where it's like, hey, let's try it with 6 rectangles instead. And that's what problem 4 is asking us to do. Let's do 6 rectangles on the lower bound, 6 rectangles on the upper bound. All right. And we're gonna approximate a new area now, finding the lower bound, what's that equal to, and the upper bound, what's that equal to. So I want you guys to work now on this part, problem 4 here, fill in this table and see what you get for your areas. And hopefully we start noticing a pattern when we add more rectangles here to see what's happening. So go ahead and try problem 4 now. This is going to be true for both parts A and B. And then we just have to figure out the height. And then we can do our, the first one, the height is 1. And then what did I have written down here? I had a 1.11, a 1.44, a 2, 2.77, 3.77. And then on the second one, it should be the same heights, just everything shifted. And you just have to figure out what the last height is. And the last one's going to be 5. And that's how I did this, and then we can do the area, adding all of these, multiplying all of these, and then adding them all together. So yeah, maybe it would be easier to do it on a table, to do, if you do an Excel spreadsheet or a Google sheet, you can do box 1 times box 2, and then you can just do the sum down here to find all of them together. But what we should be able to do now is we're using more rectangles the goal is to try and give us a better estimate. So when it says, why do you think more rectangles? It's to give us a better estimate. And that's exactly what we'll see when we do the lower bound. I think I got something like 4.03704. So hopefully you guys got something similar. It depends on how you round it. And then on the top end, I got 5.3707037. But we'll see that we're getting smaller, we're getting closer, right? Because before we had 3.75 and 5.75 as the two bounds respectively. Now we're at 4.03 and 5.37. So we're getting closer to a middle ground. All right, when we moved six rectangles in there. So as the lower, are the lower bounds and upper bounds closer? Yes, they are closer. How do you think these estimates can be improved? We can improve by adding more triangles. Or more rectangles. Okay. And it says write a new inequality. Well, the inequality is going to be the exact same. The lower bound is still less than the area, still less than the upper bound. And then the last part here, I just go ahead and we give you the numbers and say, hey, what happens when n equals 50? What happens when n equals 20? Whoops, this should be up here. This is the 50 right here. And then when n equals 100. So we have 20 triangles. This is the lower bound. Here's the upper bound. We have 50 triangles. Here's the lower bound. Here's the upper bound. We have 100 not triangles, rectangles. I keep saying triangles, sorry. 100 rectangles. This is the lower bound. This is the upper bound. All right. So what can we say happens to the lower bound as the number of rectangles increases? Is the lower bound going up or is it going down? Remember, that was always an underestimate.
It increases because it's getting closer.
Yes, exactly.
Upper bound, it gets smaller because it's getting closer.
Exactly. Increases as we add rectangles. This one decreases as we add rectangles. And then here are just some values of the lower bound and upper bound. We can see what happens if we had 500 rectangles, if we had 1,000 rectangles, if we had 10,000 rectangles. You could do this over and over and over again. So as n tends to infinity, as we go to like infinite number of rectangles, what can we say about the value of the area? Looks like the area is going to be approximately 4.667, something like that. Or when you round it up, right? Or 4.666. All right. So like, but the total area is probably about 4 2/3. That's what's happening here. All right, that's what this investigation is about. This is the classic calculus problem to find area. You build more and more rectangles. And instead of doing the rectangles over and over again, what we can do instead is we can use something called an integral. And an integral is going to be this weird symbol right here. It's going to look like an S, a music sign, something weird like that. I don't know how to describe that. But it's going to be something like that. And it's going to have A and B. A is the lower bound. Or the lower limit. B is the upper limit. All right. And the way you write this whole thing is you'd say the upper limit, the lower limit, and then you write the function, f of x, and then you write the letters dx afterwards. All right, and that gives the area of a curve from the 2 points when x equals a to when x equals b. So let's go ahead and take a look at an example real quick. Example 3 gives us this linear function. It says write down a definite integral that gives the area of the shaded region. So what we're going to want to do for this example is we'll want to write down the functions given to us as negative x plus 6. So we can write down integral, the lower bound is going to be 1 and the upper bound is going to be 4. And then we write down the function itself, negative x plus 6, and then we finish it with the dx. And the dx basically stands for like a derivative with respect to x. Essentially what we're going to do is we're going to find an integral, which is going to be like undoing a derivative. So we're going to talk about how to undo derivatives as we move into this chapter. And that's what integrals are doing. All right, they're helping us find area under curve, under functions, and they're going to help us undo derivatives. So for this one, it says find the value of the definite integral. What we're going to want to do with this now is we want to look at this as a trapezoid, just like we did on the warm-up. And we've got a height, a base of 5 there. We've got a base of 2 there. And we've got a height of 3. Okay, so so what we want to do for this one then is we want to say use our trapezoid formula. So even though we have this equation here, we're saying, oh, the integral means we want to find the area. So we're going to do the area of a trapezoid problem here. Base 1, 5, base 2 is 2, and then the height is 3. So 5 plus 2 times 3. And that comes out to 7 halves plus 3. Let's see, is that 7 halves? Yeah. So 5 plus 2 is 7. And then 7 times 3 is 21. 21 times 1 half is 10 and a half. Let's do 10.5. All right. So that's how we'd find the area. That's how you would calculate the actual integral right there for a linear function. So for a linear function, we would just actually find the area under the curve, just like that. We're going to talk about how to do nonlinear functions a little bit, but for right now, just a linear function. All right, and our last example today, example 4 says, state clearly the function being integrated, the lower limit of integration and the upper limit of integration. So first, it just says state the function. What type of function is it? Well, it's x plus 4. That's a linear function. And then to state the lower limit, x equals -1. State the upper limit, x equals 3. So we're just, for problem 4 here, example 4, just asking you to identify the key features of the integral. So what's the function? What type of function is it? X plus 4, that's a line, a straight line, a linear function. If it was like an x squared, it'd be a quadratic function. X cubed, it'd be a cubic function. And then we want to sketch the graph of it really quickly on that interval, -1 to 3, and shade the region whose area the definite integral represents. So if I were to sketch a graph, I know this is going to intercept at 4 here. And it's going to go from -1 to 3. Oops. And it'll go from there. Oops, let's draw a line here. Blue. Looks something like this up to 3. And then we can draw the vertical area here and say here's our shaded region captured by the x-axis and the two functions. That's how we would sketch a quick graph of this x plus 4. And then the last part says find the value of the definite integral by using the area formula. So if we have this this sketch drawn here, I want to say the distance here, this height of this trapezoid is 4, and then from here we're going up. It was 4, it was down 1, so this is going to be 3. Not very well drawn, but that's a 3. And then we go up 1 over 1, that's 5. Up 1 over 1, that's 6. Up 1 over 1, that's 7.
Wait, how are you doing this one right now?
Oh, I'm just looking at my terrible sketch of a graph and figuring out the height. I know the intercept is at 4 here, and the slope is 1, so I just went over 1, down 1 to find that the height's going to be 3 when I go to -1, when I go over 1 unit. And then if I go up 1 unit, I'm going to 5, over to 1, and then I'm going to 6, 2, and then 7, 3. That's how I'm kind of finding the height there. If I just sketched this on Desmos, it'd probably be even easier to do. So then the last part here, find the value of the definite integral. And that's just where we say, okay, I got, this goes from -1 to 3, x plus 4 dx. And now I just need to set up that area formula. Base 1 plus base 2 times my height. That's going to be 10 times 4 is 40, divided by 2 is 20. So that'd be the total area of this particular function. All right. So for your guys' assignment tonight,